In this video, we're going to solve a couple of problems on relative motion, and then we'll derive a formula, a general formula to calculate relative velocities. So here's situation number 1. So we have one person on bike traveling towards the right at 5 meters per second. Let's call him Akash. Then we have a second guy jogging towards the right 9 meters per second. Let's call him Bolt. And the question now is, what's the velocity of Akash as seen by Bolt with respect to Bolt? Okay, let's try to figure that out. The first thing to do is jump into Bolt's point of view. Think from Bolt's point of view. Well, Bolt will not see himself moving. I mean, when you're jogging, you don't see yourself moving. And therefore, from Bolt's point of view, Bolt is at rest. But instead, when he looks at the ground, he will see the ground traveling backwards at 9 meters per second. So that's the first thing to remember, that from Bolt's point of view, the whole ground is traveling backwards at 9 meters per second. And now the question is, what is Akash doing with respect to Bolt? To do that, we will wait for 1 second, and then we'll see where Akash ends up at the end of 1 second. Okay? So in 1 second, we will see Akash traveling forward 5 meters on the ground, because he's traveling 5 meters per second on the ground. But in that same 1 second, both Akash and the ground will travel back 9 meters. Ooh, this is what's going to happen. Okay, so let's just write that down. We see in 1 second, this biker boy goes 5 meters forward on the ground in 1 second. But in that same time, the ground will carry him back 9 meters per second. And so notice now, effectively, Akash would end up going 4 meters backward every second. And that's what Bolt will see. And therefore, we can now say velocity of Akash with respect to Bolt is 4 meters per second backwards. And the way we will write this is we will write it as V of A for Akash, velocity of Akash, as seen by Bolt. So with respect to Bolt, we have to mention that, right? We're going to write a second letter for that. The second letter represents with respect to whom we are calculating the velocity of this first fellow. And that is 4 meters per second backwards. Now, since we have front and back, and we have velocity, which depends on direction, let's use sign conventions, right? It's easier to talk in terms of plus and minus rather than forward and backward. So let's choose one direction positive. Let's choose right side as positive. Then velocity of A is positive, velocity of B is positive, but velocity of A with respect to B, VAB, this is negative because Bolt sees this fellow going backwards. So this is now minus 4 meters per second. All right, now the question is, can we build a formula for this? All right, so let's try to write this relative velocity, VAB, in terms of a formula. So to generalize this, let's say this guy is having a velocity VA towards the right. And let's say this fellow is having a velocity VB. So the question now is, what is VAB? Well, let's see what we did. What we did over here to calculate relative velocity is we actually did 5 minus 9. Okay? And that 5 is VA. So 5 minus 9. What is 9? Ooh, 9 is VB. So if you think about it, we have now just built a formula. Look at this carefully. The formula is VAB equals VA minus VB. That's a very easy, very simple formula to remember. And this formula helps you calculate velocity of A with respect to B. We'll come back to this formula a little bit later. But first what we'll do now is we'll take another example and let's see whether we can do the same thing with the second example. And here is situation number 2. Over here we have a snail traveling towards the right and a train traveling towards the left. Okay, and what we are going to do is try to find out what's the velocity of the snail with respect to the train. Okay, what I want you to do is first pause the video and try to figure this out yourself using the same exercise what we did over here. And when you're doing this, please don't look at the signs for a while. Just forget about the signs. Just do this logically and see if you can come up with the answer. All right, let's see. Let's do this logically first. The train is traveling towards the left 50 meters per second. But once you jump into the train, from the train's perspective, well, the train is not moving, it's at rest. Instead, the whole ground is moving towards the right 50 meters every second, and on that ground, the snail is traveling 2 meters per second. So if we wait for 1 second, what will the snail do? Where will the snail be? Well, in 1 second, the snail would have traveled 2 meters forward on the ground. But then the whole snail and the ground, the whole thing would have traveled 50 meters forward. Okay, notice in this case, that's happening in the same direction. Alright, so if you put that together, let's write it down somewhere. Let's write it down over here. In 1 second, we found the snail travels 2 meters every second on the ground. But in that 1 second, the ground will carry the snail forward 50 meters per second. And so notice, if you put this all together, you would see the snail effectively going forward 52 meters per second. And this now is the velocity of the snail with respect to the train. So we can now write this with the notation: velocity of the snail with respect to the train is an incredible 52 meters per second. The snail is super fast with respect to the train. And this sort of makes sense because you may have experienced this. If you're traveling in some vehicle in one direction, and if you have ever seen vehicles approaching you in the opposite direction, you may have seen them zooming very fast with respect to you. That's exactly what's going on. Okay, now let's bring in the signs. Okay, if you use signs, we will see that velocity of the snail is positive. Let's call this as Vs, and this is positive. Velocity of the train, well, that is negative because the train is traveling towards the left. That's negative. Okay, and the relative velocity, well, that is positive. And so the next thing is to build a formula. And again, I encourage you to pause this and see if you can do it yourself. All right, so please try to do this. Let's build a formula. Let's do this. Let's put them together. Okay, what is this equal to? Okay, what did we do over here? Well, what we did is 2 plus 50. 2 is the velocity of the snail. So velocity of the snail plus 50. Well, what is 50? Well, that's velocity of train. Oh, no, that's not velocity of train. That is negative of the velocity of the train, correct? So 50 is negative of velocity of train. So to this, we added negative of Vt. And so if you now put them together, we will see Vst is equal to Vs minus Vt. Ta-da! There we have it. That's our formula for the second case. So we built a formula for relative velocity of objects traveling in the same direction. We now also did that for objects traveling in the opposite direction. But if you look at them carefully, you see that we have gotten the same formula. VAB equal to VA minus VB. VST equal to Vs minus Vt. Ooh, you know what this means? We can use this as a general formula in any case we want. That's very nice. This is our general formula. Just one last thing to ponder upon is, notice in this formula, VA and VB are the velocities with respect to the ground. But it doesn't have to be ground. Let's say, let's imagine that these guys were not traveling on the ground, but let's say they were traveling on some giant treadmill, you know, some sort of a travelator or something like that. You know, imagine this, they were on this platform and the whole platform was traveling towards the right at 30,000 meters per second. Now, it might seem like the whole situation has become extremely complicated, but it hasn't. The relative velocity still remains the same. The formula still works. And the only small difference is V and VB now would be velocities with respect to the platform. Okay, and here's how I like to convince myself that this will work. Earlier when we did with respect to the ground, remember ground is a surface of the earth, and earth is actually a giant platform that's going around the sun. So there's nothing special about ground. So if this formula works for ground reference frame, it'll also work for any other point of view or any other reference frame, like the platform, or maybe they are swimming with respect to the river. Anything will do. So to summarize everything, this is the general formula to calculate relative velocity between any two objects. And when you're using the formula, make sure of two things. One, use proper signs. Their velocities are sign sensitives. And second, make sure that VA and VB or VS and VT, they are velocities with respect to some common reference frame. It doesn't have to be ground. It can be with respect to a platform. It could be with respect to a river or air, but some common reference frame.